Okay, why don't we go ahead and get started here. Happy fall spring number 2, I believe, is the current iteration. What's that? Yeah, we had a little bit of a fall spring earlier. So anyway, I'm sure we're all looking forward to mud season and second winter and stuff. So our speaker today is Salman Habib, whom I've known, I think, since 2002, something like that. Yeah. Salman got his PhD at the University of Maryland. Started off with Joe Weber, actually working on gravitational wave stuff. And did a postdoc with Bill Unruh at the University of British Columbia before heading to Los Alamos National Lab. And he started as a postdoc there, but rose through the ranks and was a senior scientist in the theory division for a number of years until 2011, when he moved to Argonne National Lab. And in 2019, he became the division director in the computational science division, and that's the post he holds now. He has a number of honors and is a well-respected computational scientist working in cosmological simulations, and so we're very interested in hearing his thoughts on large-scale computing for cosmological surveys.
Thanks, Paul. So can people hear me? Thanks very much for the invitation, and I didn't realize I was well-respected, but okay. I'm not going to argue. All right. So I'm going to tell you about what's happening in large-scale computing for cosmological surveys, and at least from what we're doing at Argonne. So this talk is somewhat of a blend of a technical seminar and a colloquium. So please feel, ask questions, and if some of the questions you can hold for later, that's fine too. But if you have any question, go ahead and ask. So obviously, when you hear a cosmology talk, there's the usual thing of dark energy, dark matter, etc. I mean, which is all fine, and obviously all of us cosmologists, that mostly the kind of things we worry about. But another completely different way of thinking about the universe, which is the way I like to think about it, is that it's just basically another dynamical system, right? It is complicated and messy, but it's basically an initial value problem, and that's what you want to do. So it is nonlinear, it's multi-physics, multi-scale, but it has some other very interesting features. For instance, it's one of the few dynamical systems that you can actually solve with some reasonable accuracy for your observables that brings together an enormous amount of physics: space-time physics, quantum mechanics, radiation, nuclear and particle physics, atomic and molecular physics, and plasma physics. So if you're a theorist who's interested in dabbling in all kinds of things, then cosmology is where you want to be. Okay? And so even though it's complicated, yet it's still comprehensible. But the interesting thing is that over time, our tools for investigating the universe improve, both observationally and as well as from the theoretical perspective and modeling and simulation-wise. So we always learn some new things, and the pace of this learning is actually quite impressive, as pretty much everyone here knows. So one question that I often ask myself is it realistic to shove or to actually be able to model the universe in a consistent manner in a supercomputer? And that's just a challenge in of itself, and aside from all the other reasons why I want to do it. So this is a very interesting challenge, and we have a pretty big cosmology group at Argonne, and so everything I'm talking about today has benefited from working with all of these people who are here. And of course, I don't have time to say exactly who it is. I should also mention that a lot of the stuff that I've done has come from collaborations over the past several years. And so I want to mention some collaborators, and including Paul Ricker. So thanks very much, Paul. And a lot of stuff that we've been doing in different areas has come from working with these people. And they're all also very interesting. And so let's move on into what this talk is actually about. So cosmology is an observational science, so that's distinct from a lot of the times you work in physics where you have predictions, you can tune experiments to your predictions, and that's not something you can do in cosmology. So it's actually quite simple, and one of the nice things about cosmology is that you can argue about a relatively small number of parameters, maybe of order 10. And the important thing about cosmology is that one of the fundamental pieces of physics or precision experiments in physics is that you have to be able to control your experiment, control the environment of your experiment, be able to repeat your experiment, be able to isolate your experiment. None of this is possible in cosmology. And that's one reason why computing becomes so important, because you have to model a lot of things because you simply can't control anything. So you have to say, okay, can I model all this stuff? And the fact that observations are often dictated by circumstances, like we live on a planet with an atmosphere that is annoyingly scattering all kinds of wavelengths, things like that. So modeling has an extremely important role. Now, cosmology also has an interesting aspect, which is that there are two kinds of paradigm shifts in science. One of them are the Kuhnian paradigm shifts, which are idea-driven revolutions, which come now and then, like quantum mechanics and general relativity. But most of the revolutions that we have are actually more evolutionary and are driven by tools. This is emphasized in a book by Gallison, and there's a nice article by Freeman Dyson in Science in 2012, which I encourage everyone to read. And cosmology has obviously features with both of these Gallisonian and Kuhnian paradigm shifts. And I think the one way of thinking about the major paradigm shift in cosmology, both observationally and in modeling, is the shift from analog to digital. It's a shift from photographic plates to CCDs and from basically pencil and paper to supercomputers. Now, the interesting thing here is that there is a joint evolution of instrumentation and computing that has made modern cosmology possible, and which is all driven by semiconductor technology. And again, all of you, this is NCSA, so obviously this is not news to anyone, but semiconductor technology has made the fastest gains of any technology humans have ever invented. And you can just look at these plots about exponential improvements in semiconductor metrics, like feature size and performance per watt of the systems that you have. And instrumentation and computing have both gained in, I would say, similar measures from this. So the recent gains in cosmology have not come from any major theoretical ideas in the sense that people woke up and said, oh, brilliant idea, let's do it. They've all come from data. And the first time the data has come, it's been annoying because our paradigm has said, no, we don't want that, but the data says, I insist. So, you have to go where the data leads. So cosmology right now is tool-driven. So a very similar situation exists in high-energy physics. I'm also in the high-energy physics division at Argonne. And in high-energy physics and cosmology, we have a scenario where we have standard models that work really well. In fact, they work annoyingly well because we know they must break. And we are trying our hardest to break them, and they're not breaking something. So anyway, in high-energy physics, the paradigm of combining theory, modeling, and computation is basically the paradigm of smashing clocks that everyone knows. You rip stuff up and look inside. Cosmology is very different because obviously you are living inside a clock in a certain sense, so you have an embedded perspective. And so whereas in high-energy physics, you kind of rewind the clock to high energies, and in cosmology, you're more like reading the memory of the clock. And both of them are interesting ways of doing science. So one of the interesting things that we've learned in cosmology is that an enormous amount of information in the expanding universe rests on the theory of structure formation. And probes of large-scale structure are where all the precision results have come from. Of course, the cosmic microwave background remains the gold standard because that's the thing we understand the best. But recently, large-scale structure, meaning the distribution of mass or distribution of galaxies, has become an extremely powerful probe. And the other interesting argument for doing something like that is that with next-generation telescopes and going with very deep spectroscopic surveys, you actually count a very large number of modes, in the universe of the density distribution. And so the advantage is that CMB is basically a 2D probe, whereas large-scale structure is a 3D probe. So if you get enough high-quality 3D modes, you can actually learn some very interesting science, which is kind of unique to large-scale structure. So this is just, this is a very general remark, but it is kind of interesting because the higher redshift you go to, the easier it is to do theoretical calculations because you're more linear, less nonlinear, and you can bring in other effective field theory techniques and so on and combine them with simulations. But some sense the simulations also get a little bit harder, as I'll describe in a little bit. So what are the science themes of cosmological surveys? So again, everyone knows this, but I'll just repeat it for perspective. So dark energy and structure growth, these are important things that we want to measure because dark energy, because we don't understand why the heck the universe is accelerating. And structure growth is a very important probe of general relativity. So we want to know is the past history of the universe suggests that gravity needs to be modified. There's a lot of, at large scales, dark matter seems to behave just as a boring object that has no interactions. And on small scales, we don't have very good observations, so you can argue about what's happening at small scales. So we'd like to figure that out. One of the very important things, of course, is the initial perturbations, like why are they so Gaussian? And are there some non-Gaussianities? Is there any hint that there's a non-trivial inflation model underneath? The other big thing with cosmology is that it's a very good probe of some foundational physics things like the neutrino mass. So everyone wants to measure the neutrino mass as accurately as possible because that affects structure growth. And there are always tensions because there's always systematics. So people are always wondering, is there a Hubble tension I should worry about? Is there a sigma S8 tension I should worry about? And it kind of comes and goes. And mostly my attention span is too long for me to worry about these things because by the time I average over them, they disappear. But but it is something to keep track of and not to do ambulance chasing, but to just understand what's going on. So the other important thing is that our measurements are really, really good now. It's kind of shockingly good. So there are some challenges on the theory side. Can you make predictions that can match how well the observers can actually measure things? And so some of the observations in cosmology are at the percent level of accuracy, clustering statistics, for example. So in order to do things as well as the observers can, you have to have simulations and theory that is at least percent level accurate, if not better. And because you want to understand these systematics from observations that I mentioned earlier, you have to put in enough physics ingredients in your simulation that you can credibly talk to an observer and say, I have this effect already in the simulation, or I can model this thing that you don't understand. So including all the observational issues. And the important thing is that computers are powerful enough that I would like to argue that you can do all of this. And if you can do all of this in one simulation, one very big advantage you have is now you have a unified approach for making synthetic skies that can address many different observations at once. So you can do CMB lensing, you can do standard beak lensing, you can do X-ray, you can do infrared, all from the same simulation. So if there's something wrong with a cosmological model in its internal consistency, you can investigate that. And this is a very, very cool thing, okay, that we can do now. So what are we actually computing? Well, one of the amazing things, which I always tell my AI friends, is that math is power, right? In these few equations that I've listed here and a bunch of other equations that are subgrid models lives the universe, right? And this is an amazing amount of informational compression that if you can only solve these equations, you get just sort of an amazing amount of knowledge. And to me, that's always been one of the fascinating things. So basically, the Laplace-Poisson equation, Euler equations, a few other things. And in cosmology, the gravity dominates at large scale, so that's where the Laplace-Poisson equation comes in, which has extremely complex solutions. I see, and Tim Williams is here. Hi, Tim. And so basically, what we have is we have a scenario where we do the gravity with the Laplace-Poisson equation. We have gas dynamics that we solve with an Euler equation. There's a ton of astrophysical effects, cooling, heating, stars, black holes, AGN, supernova feedback, and they all enter as phenomenological subgrid models because we don't have the dynamic range to do all of that science. There is, in order to do the fluid solvers have varied over time. They're adaptive mesh, there's smooth particle hydrodynamics, there's moving mesh, and many codes exist to solve these equations. And it's kind of interesting. I was reading an article by Bob Dickey, a very interesting article in 1969, and Dickey said, the universe is far too complicated a structure to be studied deductively, starting from initial conditions and solving the equations of motion. But of course, we do that all the time now. So things change, and it's important to realize that. Things have also changed in computational science quite a bit. And one of the important things to realize is that things like computational fluid dynamics are actually fairly young fields in the sense that they started in the 1950s. And initially, the idea was simply that you solve some intractable looking equation. And now that the computers have gotten a lot larger, we are not so much interested in solving some equation and getting a simple graph or a single number. We're interested in modeling extremely complex systems. So we have gone from solving what we would call mathematically hard problems to solving extremely complex problems. And this is, again, cosmology is a very interesting aspect of that. One person I knew reasonably well at Los Alamos was Frank Harlow, who basically was one of the gods of computational fluid dynamics. And Harlow said that in the 1950s and 1960s, there was a huge amount of suspicion about numerical methods. And in some sense, some of that suspicion in cosmology has also existed. And I think now that people are much less scared of simulation. So one thing I just want to point out is that the whole point of doing these end-to-end simulations or this very complex modeling scenario is or you want to be able to go from very simple initial conditions. So you start with Gaussian random fields, then you run your code forward. There's a complicated analysis chain, and there's also a bunch of synthetic catalog-like information that you get at the end. Now, things have gotten so realistic. I just want to tell people this because I find this kind of amusing. So these two figures here, one of them is an actual observation from a telescope, I think Magellan, and the other is a simulation of that observation, which has come from running this entire chain. So I used to have fun showing this to observers and say, which one is the fake one? And Tony Tyson took 10 minutes before he figured it out. He was sweating. So it's actually kind of impressive how well computers can do now. So there is, of course, a diversity of surveys, as I said earlier, all the way from things like JWST to DESI, South Pole Telescope, Rubin LSST, SphereX, which is I'm on the science team with SphereX, very interesting mission. So the important thing is for us when we're doing simulations is to basically design the simulation in such a way that we can do these multi-wavelength measurements, quote-unquote measurements, inside the simulation itself. So here's an example before I get into details of how we do that. And this is an example for Rubin Observatory's LSST. So this was done with a very large simulation that we ran with our code called the Outer Rim simulation. And then there was a galaxy catalog that was built on top of that with semi-analytic modeling for all the galaxy properties. And that simulation can also be used to show you the differences between what Rubin observations will look like and what Raman observations will look like. So before you actually do observations, you can use these extremely high quality simulations to test all your analysis pipelines on. And since you know what was put in, if there are any issues with the pipelines, you can figure out what went wrong. So all this sounds great, but then you have to ask yourself, well, how much work is it? So clearly, this is not something you can do on your laptop. And so one thing to think about is, okay, what are some numbers, just to put some numbers through the hopper. So galaxy surveys typically use bright galaxies as large-scale structured tracers, and these galaxies are hosted by halos in the 10 to the 11 solar mass range. The survey volumes tend to be quite large, in the tens to hundreds of gigaparsec cube. So if you want to have of order 100 simulation particles for something like a 10 to the 11 mass halo, you need something like 10 trillion particles in your simulation. So that's a lot of particles. And at the same time, if you're going to run a simulation that covers a survey with, let's just say, a gigaparsec or a few gigaparsec on the side, but you want to resolve down to a kiloparsec, you need a resolution range of 1 million. The largest scale to the smallest scale that you need to resolve everywhere in the box is of order 10 to the 6th. So imagine a simulation that is 10 to the 6th cube in dynamic range. So these numbers stress very heavily even systems that are in the exascale supercomputing class, and they require a lot of thought. So what we did was we were part of DOE's exascale computing project, which ran from 2016 to 2024, and in those 8 years, we built a code designed to run on exascale machines. So this leads us to a slight digression, which is that there are two ways to think about how to do supercomputing. One is you start at the bottom, which is the thing that Feynman emphasized. And another thing is to start at the top, because a lot of people basically don't realize that there's a huge amount of speed up possible in simply how you write code. There's a very amusing article by Lilerson et al. In 2020, which basically look at if you naively did Python on a 4K by 4K matrix multiplication, and instead you did AVX intrinsics and C, the relative speed up is something, absolute speed up is something like 62,000 times. Okay, so it means that it's good to have a fast computer, but it's also good to think. So the important rule is you should follow architecture trends and maintain a good flexibility approach to deal with the hardware. So it's always, talks are always about looking forward, but also it's interesting to look backwards, especially in computing, because the field moves so quickly that we often tend to forget our past. So in the 1990s, Moore's law was there, life was good. You didn't need to worry about speeding up your code because the computers were, twice as fast every year. So what the heck, right? Parallelism was not very difficult to deal with. There were really nice CPUs like the DEC Alpha. And then, things in the mid-2020s, the device level gains have faded, more or less. We are still stuck at a gigahertz, and yes, there's a lot more cores, but the computing advances have mostly fragmented, and things have become more heterogeneous. You have now looking at all the power coming from GPUs. And with the power wall that we have hit right now in computing, and not everyone can afford to spend 100 megawatts on a system, you have to confront the future, which may be much more specialized, where you might have a machine like Anton, which was built by D.E. Shaw Research for protein folding. So you might imagine more specialized systems. So at any rate, it's kind of an interesting future to contemplate. The other digression that I have here is about supercomputers. So I've spent a large chunk of my career dealing with these beasts. And I would say they are kind of fascinating in the sense that they are a huge pain. And programming them and debugging codes is very, very tedious. The interactivity is very poor because you are fighting with a lot of other people to get time on the system. The file systems still are terrible. They eat your data or refuse to move it. And the machines are really designed for large-scale computing. They're not really designed for large-scale data analytics. So you have to figure out how to do that. They have a high failure rate. Every vendor says, oh, yeah, don't worry. But their failure rate is like every time you run a code, within an hour or two, something bad happens. So you have to be able to write code in such a way that is extremely resilient. At the same time, there are amazing things. There are some problems that you cannot do otherwise. So to me, that's why we work on systems like Aurora. And my initial supercomputer that I worked on was a thinking machine CM5, which is still my favorite machine. And the cabinet design was by Maya Lin, by the way. So kind of an interesting thing. So supercomputers are amazing because they can lead to scientific insights you can not have otherwise. And the current systems that we are running stuff on are the new exascale machines, or new-ish. Frontier at Oak Ridge, Aurora at Argonne, El Capitan at Livermore. These are all GPU-accelerated systems. And over time, our code is now, when we started, before the pre-exascale era, when we started improving our code to the exascale era, the performance gain was about a factor of 200. So that is really quite substantial. So the beginnings of the hack code, which is the hardware-accelerated cosmology code, is that initially started off from a code that Rob Ryan and I wrote together in 1996 to do beam physics. And then a lot of stuff happened after that. And I should just quickly run the simulation to give you an idea of this dynamic range thing that I was talking about. So when you do a cosmology simulation, this is a Q continuum run on Titan at Oak Ridge, which has 16,000 GPUs. And so initially, the universe starts very, very homogeneous, and then develops all this structure. And this is the result of this is a gigaparsec box simulation, and you're seeing only a very, very small piece of it. And the interesting thing is that initially it just looks like smoke settling, and then you see all the beautiful cosmic web structures appear. And the nodes are where all the galaxies form. So one of the interesting things about building the hack code is that it's extremely important to understand how helpful scale separation ideas are in cosmology. The fact that there's a large-scale force solver that you can use, that you can employ using Poisson solvers, and on small scales you can do direct force summation. You can do some very clever tricks about how to isolate the long-range from the short-range forces, how to couple them together, how to do task-based load balancing. I don't have the time to explain all of that, but that is what took us several years of working to fix it. And one of the things that we've done, one of the things we're very interested in, is that we understand that this is a lot of work and not everyone wants to do it. So one of the things we're doing right now is we're making all the data that we get from running the simulations publicly available. And more importantly, we're writing an analysis framework that people can run on that data that will run automatically on our machines, so they don't even have to know how to run on the machines. So this is a project called Open Cosmo, and I'll say a bit more about that. So the other important thing in cosmological simulations is the gas, and there's historically been a huge amount of fighting between the AMR people and the SPH people, and I've seen people almost come to blows on this question of what method they should be using. So we use a next generation smooth particle hydrodynamics method, and SPH is very cool because it has all these nice properties of invariance and geometric adaptivity, but it also has serious problems with errors. So we use a method called conservative reproducing kernel SPH, which was Nick Frontieri's PhD thesis, and was work that he did with Mike Cohen and Chris Raskin at Livermore. He spent one summer there, and that's where all the ideas came from. This is an extremely interesting method. And after this method and a couple other methods that have improved this situation, it can be said now that there are no more differences in cosmology simulations between SPH and AMR. We recently ran a comparison between our code and an AMR code called NIX, which is developed completely independently by people at Berkeley, and the errors are within 1%. I mean, the differences. Which is not to say that, there could be, that's a relative error, not absolute, but still is very comforting that these things agree so well. The other thing is how do these codes actually work? As I said, the dynamic range is amazing, right? 10 to the 6. So this is sort of an example. You have the long-range spectral solver as a 12,600 cube grid FFT. And actually, we can do FFTs up to 30,000 cube if we want. But for this particular run, which was a Frontier E run at Oak Ridge, which was done on 36,000 GPUs, and it's the world's largest hydro simulation ever. And then what happens is from this big thing, you go down to smaller grids, and then to an even smaller scale, and there the grids break up into these sort of adaptive domains, which are based on tree ideas. And all of this looks like some sort of Rube Goldberg contraption when you look at it, but there's actual math behind it. And there's a lot of theory behind how the error patterns move and how the error diffuses from one range to the other. So one of the important things about this is that, as I said, the machines are not very resilient. And they break down all the time. So you have to have extremely fast output to your file systems. So because each time, if you're running and the machine is crashing, then you want to have checkpoints that you layer so that you have an output. If the machine crashes, you can go back to that and start again. And so we have worked really, really hard on solving this multi-tiered I/O problem, and we get effective rates of data transfer in the multiple terabytes per second. And this has been essential to being able to do these very long runs. So for example, this run, the Frontier E run, took weeks on the full machine of Frontier. And during that run, I think we wrote something like 100 petabytes of file. So now that you have this, you can ask yourself, what can you do with these very large simulations where you have such enormous amounts of information? So you get an enormous amount of simulation products. You get, the clumps of matter, the halos, and you also have the substructure. We have an on-the-fly light cone, so we have the full, light cone up to, in this Frontier E, up to a redshift of 1.5 without replication. And you can do a lot of stuff on galaxy halo connection, including machine learning methods, galaxy property inclusion. We have things like metallicity, dust attenuation, SEDs, everything. And then you can do benchmarking all of that using survey data. So of course, there's some complicated workflow always about how to do that. But the point I'm trying to make is it's not about just solving equations. It's also about building the infrastructure to do analysis. So one example of this is that we recently did an all-sky synthetic catalog for SphereX, which is a near-infrared mission. And we have narrowband SEDs simulated for sphere-X, and this is a paper led by Nesar Ramachandra, which will hopefully be out there soon. And it's a full sky redshift range from 0 to 5, has all 100 million galaxies or more. And so there's this whole, I would say, enterprise of producing synthetic sky mocks, which you can also use for inverse problems. But I won't have time to talk about that. The other thing, very interesting thing you can do with simulations is that you can make predictions for nonlinear quantities that are otherwise extremely difficult. And we worked a lot with statisticians to develop what are these things are called emulators. So now they've become like completely standard in the field. And if you say emulators, people say, well, everyone does that. But when we started doing emulators, everyone said this is crazy, it'll never work. And the idea here is to run some simulations across a certain small set of parameters, maybe of order 10, maybe order 20. And you sample the parameters, and then maybe you have an output for, say, the bar spectrum or the mass function or some other observable. And then you build an interesting interpolation method that says, if I change the parameters, what should the answer be? And there's a technology that we developed to do this with dimensional reduction, with PCA and other techniques, with Gaussian processes and so on, and the inverse problem then being solved by MCMC. So this is also very interesting because it allows you to then make predictions in a forward model sense for a lot of observables, like the power spectrum over here, the mass function, which was used by the South Pole Telescope, for example. And there are other predictions for weak lensing, and these are all accuracies of about 1%. So now you have not only the ability to create a synthetic sky, but the ability to create a predictive tool, which is very accurate to about 1% or so. And the same emulation technology can also be used in these hydro simulations, because in a hydro simulation, you have a bunch of subgrid models. And the subgrid models are the most dangerous part, because they are basically often coming from relatively simplistic assumptions, and we are not often sure about how good the assumptions are. And we are not sure what the values of the subgrid modeling parameters should be. For example, there are situations about, how do we model AGN feedback? Well, we are not really certain about that. There are modes of AGN feedback. Are we treating one mode correctly and not the other mode, and so on? So we want to be able to understand the effects of changing all these parameters. And historically, this was done more or less by seat of the pants, meaning you ran a bunch of simulation, you said, I think, and something like that. It was literally like humans trying to guess. But now we made this completely systematic, and there's a paper that we put out there. And we're working on ways of making the calibration process something that is actually statistically controlled and not just guessed at. So now I want to just describe one of this big simulation, the Frontier E simulation, and just so that you get an idea of what's possible with these large-scale simulations. So here's what it is. The box size is 3 gigaparsec. And the total data set right now, after throwing away all the extraneous things, because the facilities don't allow us to store as much as we want, so they let us keep 12 petabytes of data. So it has 4 trillion particles in dark matter and tracers, and the same, and in baryonic tracers. The mass resolution in the baryons is 2 times 10 to the 8. We have 2,000 clusters with masses above 10 to the 15. We have 500,000 clusters. Observers can never, ever match us, okay? But it means that the statistics are so good that you can do all kinds of analyses, which you simply cannot do otherwise. We have a full sky particle light cone out to Z of 3, and we have complete particles in the simulation particles for all halos of mass above this. We have merger trees for all the halos and galaxies. We have about 1 billion galaxies at Z of 0. And the synthetic sky catalogs have been generated using a number of methods. So this is just an example picture of a merging halo, but I will now walk you through a bunch of results. So the included physics is important to note. So obviously we have UV background and metal line cooling. These are all like subgrid models. We have chemical enrichment, star formation and supernova feedback, AGN thermal and kinetic feedback modes. And all of these subgrid models are calibrated in all simulations. And one of the interesting things is, what do you calibrate on? And this is an argument that goes back and forth among the simulators. So we chose to calibrate on the galaxy stellar mass function across redshift and on cluster gas density profiles. Because we have so many clusters, we can actually do a good job of calibrating based on those observables. Just using these 2 observables, we have extremely good calibration, and I'll show you some of this stuff. And so here's an example of the galaxy stellar mass function. So the solid curve here is from something called universe machine, which is in this paper. And universe machine is essentially an empirical fit to data. So it kind of is a proxy for data. And then the orange points are from Driver et al., which is a data set. There are many other data sets that we didn't show here, otherwise it makes everything look complicated. And the frontier E results are redshift 0 to redshift 2.5. And in intermediate redshifts, it also works extremely well. So the calibrated galaxy stellar mass function is really good, but to be fair, we calibrated on that, so it would be unsurprising in some sense. There's also, we have full sky maps for all kinds of observables, like the kinetic SZ, the thermal SZ, X-ray skies, the density fields. I'm just showing one or two examples here. And this is at redshift 0.25, but of course there are others. We also have all kinds of mock observations that are postage stamp observations, meaning if we find an interesting object, like a cluster, then we can go and do measurements of that cluster. So for example, here's a thermal SZ of a cluster, Compton Y. Here's the density, here's the X-ray flux, and we can split the X-ray flux into hard and soft and other things. And here's a kinetic SZ Doppler B. So all of this is sitting in that simulation, and we are obviously, many of the analyses we do ourselves, and many of the analyses we dearly love collaborators, to have collaborators to help us do. Here's another one, which is actually quite interesting, is the matter power spectrum. So what happens in the matter power spectrum is that, so this is the primordial part, and then, there's a linear part of the power spectrum, and then there's a nonlinear increase in the power spectrum. And the power spectrum, this is broken up into components. So the matter component, the gas component, the total matter component, and this is the linear part. So one of the interesting questions is, when you have gravity-only effects compared to baryonic effects, what happens to the power spectrum? The power spectrum is kind of the key measurable in large-scale structural surveys. Usually, the galaxies are used as a tracer, but here I'm not showing you the galaxy power spectrum. I'm showing you the matter power spectrum itself. And this is a ratio of the actual power spectrum in our simulations divided by what you would get if you had a gravity-only simulation. So if the results were identical, then you would get 0 over here. So at large scales, you see that baryonic effects are negligible. But at scales of around 0.2, 0.3, you start seeing effects. And this is all coming from the different feedback models that are used in simulations. So if you have a lot of feedback, like the first illustris, there's a huge dip, right, 30%. And then different models have different amounts of dips. So Flamingo, which is another large box simulation, has a much more significant dip than us. So ours is a black curve. And so this is an interesting area where simulators are trying to figure out what's going on. And clearly, there's a lot of discrepancy. And this is not coming from the solvers. This is coming from the subgrid models. So this is a place where observations and simulations will have to work together to understand what's going on. The other interesting thing, and here's another observable, and this is an observable which is a cluster gas density profile, which is something that uniquely in our simulation we can measure really well because we have so many of these clusters. And we can split it into cool core and non-cool core and make measurements and compare against measurements. I don't have time to explain all this. But the important thing, as you can see, is that we are not calibrating on this, but it seems to work really well. We don't see any issues. The other interesting thing that we can do, because we have so many interesting objects, is that we can go look for them. And so this is kind of an amusing story. So some of these objects were just found by accident. So I told Will Hicks, who's one of our postdocs, I said, I want to find some interesting things like bullet clusters. Go look for bullets. So here's one, right? So a bullet cluster is obviously when you have a merger with two clusters going through each other. There's a shock front. Yes, it's very, very pretty. And there's a temperature, right, profile. The dark matter is here. The stars are doing their thing. But now, so this was just by chance that Will found it. But obviously, it would be torture to say, go look at 570,000 objects. And so we have written an agentic, so we wrote an agentic AI toolkit. Basically, we said to it, the prompt was, read the literature and find what a good metric is for finding interesting objects of this kind. Come back and run through the code. So so that is something that has reached a pretty high level of sophistication now. I mean, I have another movie, but it's not complete yet. But the nice thing is that it works really well, and it enables you to do all kinds of things that otherwise you wouldn't be able to do. For example, we can do things like we can say, okay, find all the relaxed halos, and then do tests to see, even in the relaxed halo, are there circumstances in which the gas is relaxed, but the gas is not relaxed? And if so, why is that? And what is the stellar population doing in these things? So there's a lot of sub-studies you can do, which would be extremely painful by simply asking the agent to do the running around for you. So I mean, I hesitate to say that this will replace grad students, because clearly it won't, but it will make life much more fun for grad students, right? Because you can wake up one morning and say, I can do that. And while you're showering, the agent has done it for you, right? So this is really cool. I'm very, very happy about this kind of thing. So, and it also means that even people with very little time like me can, do things, because we don't have to sit down and go through some many, many lines of code. You can just actually do this very quickly. So now I just want to show a movie of the Frontier E simulation, just so people get an idea of what it actually looks like. So this is a small chunk of it, a 64 H inverse megaparsec box, and we are zooming into a cluster, which has, and this is what the gas temperature is the gas density, this is the stars, stellar density, and there's a dark matter density. This is 100,000th of the volume of the simulation, so it's a tiny piece of the universe. And this movie was made by J.D. Emberson, and for some interesting reason, it's called the Ember cluster. But yeah, so this cluster even has a name. So you can imagine now that there are many such objects inside the simulation volume, and you can get detailed information about all of them. So it literally is like running a survey in your computer, which is what I was interested in from the beginning, is can I stuff the universe inside a computer with all its complexity and in ways that are actually realistic. I mean, we are actually comparing with a ton of observations, and only one, which is the gas fraction in halos, am I a little bit nervous about. And at that point, I'm not sure I trust E Rosita results yet. But everything else seems to work really well. Okay, so I think I'll stop there, and this is my last slide. And this is basically that, essentially now, it's a digression on the future of tools, right? So large-scale computing shows no signs of slowing down yet. I mean, clearly machines are going to become more expensive and eat more power. There's no question about that. But they are not going to go away. We will have powerful computers. The other interesting thing is that AI ML tools are getting a lot better. Personally, I live between two domains of being skeptical on the one hand of certain kinds of things, like foundation models I don't believe in, but agentic systems I have great faith in, with using tools that are controlled. And the reason I don't like foundation models is they're opaque, and I don't like things that are opaque. So the other interesting thing is that the data sets that we have are massive and realistic, and so they're extremely good for training a whole bunch of things, as long as you're careful about how you're doing your training and what it's for. There is a new generation of physics-rich emulators that will address a lot of the end-to-end survey modeling and systematics issues, and I think that's going to be, from my point of view, something very interesting in the next few years. The other thing that the field is very excited about is what's called field-level inference. Like the way we normally did inference in cosmology was to take an observable, statistical observable like CLs in CMB or power spectra in large-scale structure, two-point correlation functions, and did inverse problems with those scalar things. But now people want to do inverse problems by basically predicting the distribution of a single snapshot of the universe and then working backwards from that. So this is something called field-level inference. It's optimal in the sense that all the information you have, you can use in field-level inference. It's also extremely dangerous because it is not robust at all. And so this is something that is a lesson to be learned from control theory from the 1970s. Initially, control theorists were very, how should I say, optimistic about optimal control. And then they discovered that optimal control can be extremely dangerous. And then robust control came in the 1980s. driven by work by John Doyle and others. And so the important and interesting question is, how can we do field-level inference, but tempered by a robustness paradigm? So that is something that I'm very interested in. And we'll see, how well all that works. Then I promise I'll tell you a bit about OpenCosmo. So OpenCosmo aims to provide easy access to all of these results, and we're working very hard to make it happen. We are very, very interested in having early-stage people look at this. The first release is imminent. I think Patrick Wells, and Michael Bielman, who are the two leaders on this, will have this thing out very soon. And LSST Desk is obviously hopefully one of the major users of this. And we are very interested in collaborating on this. So we want to give people who are interested in working with us early access and ability to run analysis on a simulated universe. So with that, thank you. I'm happy to be here.
Before we do questions, two announcements. So Salman is going to give NCSA colloquium at 3 here on Just Computing. And then at 4 in the atrium, we'll do like kind of office hours. So if you want to come talk to him, he's there. He would love it if you came and asked for a letter of recommendation or a job.
Hi, thanks for the nice talk. I was thinking about the simulation that you showed that is like 3 gigaparsec.
Yes.
And you also showed that it's like that you can have a huge amount of resolution in that. So I was wondering, is it done everything on the fly? Do you have that amount of resolution for every single object in that simulation?
Yeah, we do.
It's crazy how different it is, how improved it is from like a 300 megaparsec illustrious TNG, right?
Yeah.
Could you comment like why you think it was like the main differences that allowed you to?
Oh no, it's a very good question. So I didn't want to say too much about the computing side. It's all driven by the GPUs. So if you do an analysis and you ask yourself, suppose you wanted to run a TNG simulation with their code, in principle you can do it. It would take you a year of all the CPUs on Frontier. It took us a week. So there's a 50x performance factor by running our code. The code is actually blazingly fast. I mean, I don't want to, I'm happy to take credit for it because Nick and the others put a lot of effort into optimizing it, but it is really very, very fast. That's the difference. Yeah.
Really nice.
There was one point where you were talking about the difficulty of getting the data basically out of RAM and onto the hard disks when you're taking snapshots. That sounds really similar to what I assume a lot of, even in astronomy, like instrumentalists or researchers that are actually taking data have had to deal with for a long time, and not necessarily at the Vera Rubin scale. But was this something you innovated independently of instrumentation, or did you take some of their?
This is way harder than the people in instrumentation have to deal with. I mean, they're talking about 30 terabytes a night. We are talking, terabytes we are talking of order 10, 20 terabytes per second.
Okay, so it wasn't the platform, is that it really was higher than any kind of instrumentation.
Oh yeah,
bandwidth.
yeah. I mean, this is much higher than any instrumentation, and so people in supercomputing or high performance computing in general have worried about this kind of issue forever, and there have been all kinds of techniques to try and speed up this business of moving from RAM to the file system. This has traditionally been a kind of weak point of supercomputing, this bandwidth and latency for I/O, and historically, it wasn't so much of a problem because the machines were relatively stable. But now that we have to do checkpointing so often, the thing that is a limit on I/O historically was how much do you want to store, right? Now it's how fast you want to run the simulation because this has become a choke point. So on Frontier, we managed to get around it because we are using NVRAM that Frontier also has. So basically what you do is you take your data off RAM, shove it onto NVRAM, and that's very quick. Then go back to running a simulation, and then bleed the data from the NVRAM off to disk. So that way we got got a performance that was actually faster than the best performance you can get on the file system. And I mean, this is not rocket science. People can do it, but it just is something you have to pay attention to.
So I had a question about the scale, right? So going back to what you were asking. So roughly you have 3 gigaparsecs of volume.
Yeah.
And the observable universe is around 14, 16?
Yeah, I mean,
so we're talking
depends on how
about
yeah, so this is basically
20%, 30%
so if you
of...
look, yeah, the way to think about it, the way I like to think about it is that with this size of a box, 3 GPC over H, so 5 GPC, you can go to, the light cone goes to redshift of 1.5 without replication. Okay, if you want to go deeper, you have to replicate. So if you wanted, so something like SphereX, which is an all-sky survey, the box we ran, actually we just finished doing that run, which is the world's largest gravity-only simulation. That I think is 9 gigaparsec.
Okay.
So pretty.
And I wanted to have a comparison with what people have been doing in the last decade or so, which was, early on was this Millennium simulation, and then they have things like Illustrious. But those are orders of magnitude smaller than what you're presenting right now.
I think, yeah, so I think there's a...
I think that, it will be good for most of the folks who have then an idea of how large this is compared to what happened before.
So there are interesting questions here. So it's not a simple matter of volume, because because a lot of people are not necessarily interested in cosmology. They're also interested in things like galaxy formation and astrophysics, and they need to put in a lot more physics, like nuclear chemistry, chains, et cetera, et cetera. So then what happens is you have to make time steps that are much, much shorter. And your resolutions have to go down to something like a parsec scale. So one thing I didn't mention is that we do all of that by subgrid models. So we cheat, right? So what we do is we rely on people who do very high resolution simulations. So we work with Claude-André Faucher-Gregeur, who is a member of a team called FIRE. And FIRE builds one galaxy at a time. And so it's totally unfair to compare our stuff with FIRE, because they are running very high resolution simulations in smaller boxes because it takes so much time. But what they learn, we feed into our subgrid models, right? So if you look at things like Millennium and other simulations that were run in the hundreds of megaparsec, well, Millennium was an n-body code, but the hydro codes are about typically 10 to 30 times slower than the gravity-only codes. And we are now at a point where with GPUs, and ours, I think, still the only GPU, large-scale, scalable GPU code, we are at the point where a hydro code can match the state-of-the-art n-body code in terms of volume and resolution, which previously people couldn't do because of this factor of 10 to 30. So that I think is the right way to kind of think about it. I try not to compare too much because everything is also driven by compute power. Flops is flops after all. So if you look at codes that were run 5 or 6 years ago, they were heroic things then, and it's not really fair to compare to them now. But I think a lot of very interesting things are happening. I was at Santa Barbara a couple of weeks ago in a meeting with Stefano and Joop, who are people who run very large hydro simulations, and there's so much more work and interesting things to do still.
And now the astrophysics question that I had was, in the past, as observers, and you want to know or make statistics about the number of clusters in the universe of something, you needed to rely on usually on mass functions, which were not coming from observables because you actually have never been able to observe that. So then you would need to have some good guesses that are coming nearly all of the time from simulations, right? You have these universal mass functions. But those universal mass functions usually have issues of lack of good statistics because they were not representative of the universe.
Correct.
So can you tell us now that we're in a much better shape?
Right, so we are in much better shape now. So because of these large volumes, you can certainly do cluster abundance much better. The other thing which is also very interesting is that you can study the systematic errors in measuring masses, right? And people often had, when they said we have a universal mass function, you said, well, mass function for what? FOF halos, SO halos, none of those things are actually measured, right? So now we are at the point where we say to the observer, you tell me how you're going to measure something like mass. It could be an aperture mass, it could be a lensing mass, it could be an X-ray mass. We can measure the exact same thing here and say, this is the prediction for that observable, not some idealized universal thing, which A, you don't know what it's for, and B, it's off by 10, 20% anyway. So that, I think, is the big win. Yeah.
Can you hear me? Yeah. I'm a control theorist by training, and actually I know John Doyle. So I was curious about, is there a connection between H-infinity robust control theory and what you're doing, or is it more at a...
I mean, H-infinity control directly. I mean, I actually wrote a paper with John, so we should talk about it.
Okay.
No, but there is basically a bias variance trade-off, which is very similar to what happens in control.
Okay.
So the more you go on the optimal side, the more you worry about bias, right? And you have to trade it off against variance. So when you solve these inverse problems, which is similar to the control loop, you know, in feedback control, that's where it enters.
Okay. Okay, thanks.
Thanks for a great talk. So it seems like you've reached this box size that,
Yes.
I mean, it doesn't make sense to go much bigger than this.
No.
So what do you see as the next things to improve better resolution so you could do more like fire-like simulations within that volume?
I don't know if you want to do okay, honestly, so I'm a cosmologist, right? So I have no real interest in looking into galaxy dirt, right? So I am much more interested in things that are either discovery, like protoclusters or JWST weirdo objects, right? I'm not so interested in, you know, did I get a polar ring galaxy, or, you know, it's nice, but okay. So there's that. So I think there's still a lot to be worried about in this scenario right now with the hydro simulations that everyone is running. There is a serious mismatch between the thermal SD power spectrum and simulations. I suspect it's because the thermal SD power spectrum is not as well measured as people think because of CIB background and other such issues. There is also this question of E Rosita F gas that is a concern, because some people have calibrated to low F gas values, which I think is wrong, okay, because it screws up scaling relations for clusters, and I believe in scaling relations, and our code bang on gets the scaling relation. I wish I could show the scaling relation. I didn't have them here, but they're just perfect. So there are these internal issues that simulators have to agree on. So what is also interesting is that people want to go to higher resolution. And I'm all for going to higher resolution, but then you get even more free parameters, right? Because now your subgrid models become more complex, and the more complex they get, it doesn't help. So for example, the Flamingo folks, Yop's group, recently ran a simulation, I think Colibre or something it's called, which is much higher resolution, a very, very nice simulation, but it's no better than the lower resolution simulation that has been tuned. So subgrid models are phenomenologies, and we need to understand what's robust and what's not robust about them. So one way of thinking about it is like, take, for example, Ohm's law, right? Doesn't matter what your conductor is. It can have all kinds of nonlinear crap going on underneath, but V is equal to Ri, okay? So what we want to do is to have predictions that are that robust, where we say, yeah, the subgrid model could be, but scaling law perfect. So it's that kind of thing that we want to understand, like why is it that some things are working and some things are not working?
I have one final question. You talked about the stellar mass function in the match in the simulation. You brought up CIB. How does it match the CIB?
We haven't run the CIB stuff yet, and that because we are not quite sure about how to basically even model the CIB right now. So because I mean the infrared background is like not so simple. There are many things we don't know how to model. For example, AGNs as sources, right? Because what we have is we can see what the hot gas around the AGN is doing. But the actual hard emission from the AGN, which is sub-parsec, I mean, that is no way, right? So for that, usually what you have to do, you have to build an empirical model based on some halo modeling idea and shove it in the code. But at that point, it's not predictive, right? That's just a thing that you've done. So there is one of the interesting things about all of these simulations is you have to be very careful about what is predictive, what is not predictive. And I have a hard time talking to some observers who basically think all of this is theory. It is not theory. It is modeling, right? Which are two completely different worlds. So people say, oh, there was a theory error. No, it is not a theory error. The theory is just fine. The model isn't working, you know. So we have to basically fix the model. That's what Paul's question is about.
Okay, so
Yeah.
someone will be here for the next meeting in 30 minutes if you want to ask questions. Let's let people go, and thank you.
Thank you.